Hi, I'm Charlie Jackson. I'm chair of the IEEE Online Forum on Climate Change Technologies. I'd like to thank you all for joining us today for the last day of the forum. Today we are lucky to have Dr. Maria Smolander speak on sustainability of flexible electronics. She is a research team leader of the Flexible Sensors and Devices research team at VTT Technical Research Center of Finland. Her expertise includes sustainable solutions in printed and hybrid electronics and photonics, developing and testing of printed indicator and sensor concepts, as well as printed power sources. Maria Smolander gained her PhD from the Helsinki University of Technology and has been involved as a project manager in several EU and national projects dealing with functional solutions and power sources for different applications. Recently, she has led VTT-funded activity on sustainable printed and hybrid electronics and acted as the member of the executive board and work package leader of Flexible Electronics in Graphene Flagship, the biggest research initiative in Europe. Maria, if you could give us your presentation.
Okay, thank you very much, Charlie. Yes, good morning, everyone, and or good afternoon if you happen to be on this side of the ocean. So I'm from Finland, indeed, and I will be talking about sustainability of flexible electronics. And I come from VTT, and VTT, as Charlie already mentioned, means Technical Research Center of Finland, and it's a multidisciplinary research organization. And we are tackling the grand challenges, among these the climate change and sustainability. And we are about 2,300 employees at VTT. We are a governmental non-profit research organization, and it's very typical for the work carried out at VTT that we are combining the different disciplines of technology. So we have divided the activities into 3 business areas: carbon neutral solutions, digital technologies, and sustainable products and materials. The flexible and printed electronics is in this digital technologies business area, but we are collaborating a lot with our colleagues in the sustainable products and materials. They are producing materials what we are using. And on the other hand, we are also working with the colleagues in the carbon neutral solutions. They are, for instance, applying the battery solutions what we are developing on cell level in our research area. They are applying those for mobility, for instance. So this very shortly about VTT. And indeed, as said, we have been really tackling the sustainability and also the sustainability of flexible electronics already for a couple of years, and we are very motivated to do that. And this is, of course, because we, as everybody else as well, see that all the time the amount of electronic devices in the society is increasing. We need electronics for digital transition, for connectivity, for different household applications, transportation, applications in health and well-being. And of course, this increasing amount of devices is also bringing us or around us more and more electronic waste. And for instance, between the years 2010 and 2022, the amount of e-waste almost doubled. And at the moment, a bit more than 20% of the e-waste is formally properly collected and recycled. And this recycling rate is increasing all the time, but because the amount of waste is increasing so rapidly, the waste generation is outpacing the recycling rate. So all the time we are accumulating more and more waste around us. And also today, especially in the current political situation and in the unsecure times the supply chains are not as secured anymore as they used to be. So it might be that some critical raw materials are not available, and of course some of the raw materials are even they are not, let's say, the sources are not infinite. So the circularity of raw materials is very important, and we want to look at these challenges in the development of flexible sustainable electronics. And we've tried to take a kind of like holistic approach towards the sustainability of flexible electronics, and we want to look the whole chain from the product design through the material selections and process selections to the use phase and end of life or the disposal phase of the product. So basically we see that in the design there are possibilities in selection of powering solutions, design of modular products which can be partially recycled. Regarding materials, we can select like renewable, abundant raw materials wherever possible. Regarding processes, printing, which is like a main production method in the flexible electronics, that is additive manufacturing, which is as such a beneficial characteristics for the manufacturing as it is very material efficient, and also the use of energy is also relatively low. And then of course we want to develop solutions which also increase the sustainability at the use phase, and then also what should be done and what needs to be taken into account is then the end of life strategy. So how to design products which can be partially recycled, and if not, then how are they fitting into the existing waste streams? So how could the existing processes be exploited? And basically, of course, the environmental sustainability is important, but we also want to take into account the social and economical sustainability. And for instance, the social sustainability is important when you are thinking about the use phase and the purpose of the products, what are developed, and basically we want to make sustainable selections all the way from the material selections to the integrated electronic systems. So this is let's say the overall picture of our holistic approach to sustainable flexible electronics. And I already mentioned in the beginning that the circularity is the key, because we are indeed running out of some necessary critical raw materials. So it's important to keep the materials in use. So traditionally, in linear economy, we start from raw materials, go from design to manufacturing, distribution, consumption, end of life, and then eventually the products are ended up to landfill or incineration, or kind of they end up as waste, and the materials are not necessarily anymore reused. But and this is of course not so good, but of course it would be more beneficial, let's say, when you can repair the items, when you can recycle either the raw materials or maybe even the components. You don't need to go all the way to the raw materials, so you can maybe disintegrate some of the components and remanufacture them, reuse the components. So this is also saving energy and resources. So it's important to keep the products and materials in use. And of course, in the first place, we need to think about that. Do we even need the new items all the time, and we should consider our consumption as well. But this is kind of like something what we are aiming to support in the design phase, and try to design products which are compatible with this circular thinking. So as we have now seen, this sustainability and circularity of electronics, even of flexible electronics, it's a very, very wide matter, and it's very important to join forces to develop new solutions. And one example of joint activities in this field is a project called Sustronics, Sustainable and Green Electronics for Circular Economy. So this is a CHIPS joint undertaking project, European project, and it's coordinated by Philips in the Netherlands, the company, but VDD is here the technical manager. And all in all, in this project, which is now in halfway, we have over 40 partners from 11 countries, and the budget is almost 40 million euros. And basically, the work here is arranged into 3 bigger use cases. Each of these contain different pilots, but the focus areas are circularity of electronic devices, meaning like conventional rigid electronics in this case. Then the sustainable manufacturing for electronics. This is quite a lot related to flexible electronics, and also environmentally compatible single-use electronics is handled as one use case here. And this is indeed, as I said, now halfway, and we are now starting to get results, and it looks really nice, and I'm sure that I will be able to talk about this project also in the later events. But then I already mentioned that we are focusing at VTT on the flexible electronics, printed and hybrid electronics, and for that purpose we actually are having a very nice production facility, a reel-to-reel production facility for sustainable manufacturing of printed and hybrid electronics. So basically it's like a reel-to-reel line for printing, hot embossing, then we can laminate, we can post-process. We also have like possibility to for hybrid assembly of components, and this is all possible to do in a reel-to-reel process. So basically you can get like a huge role of the electronic devices as the outcome from these processes. And why we want to work with this reel-to-reel process and this kind of flexible electronics? So as already mentioned, it's an additive manufacturing method, pretty material efficient, environmentally sustainable in that sense, but there are also other benefits like freedom for different designs, new form factors. It's compatible with large area product design, product architectures. Even stretchable materials can be used as printing substrates. We can generate like different wearable electronic devices. Sometimes the product structures can be simplified. You can integrate the electronics into mechanical parts of the products, and this means that there is less separate parts of the item, and this is resulting to reduce product volume and thickness and weight, which is as well sustainable as the manufacturing method itself. And also the reel-to-reel production methods, the printing methods, they are compatible with a huge variety of different printing substrates, and this means that we can even exploit materials which are renewable and sustainable in that sense. And when we go to let's say high volumes high enough volumes, then the manufacturing is also cost efficient. So this is kind of like our key operation on flexible electronics. And we already a couple of years ago we started on national level in a project called Ecotronics. And in this project, we collaborated with Finnish universities. And here we were in collaboration with the Lappeenranta University of Technology, or they carried out the LCA work. We wanted to compare indeed that what is the environmental impact of printing in comparison to traditional FR4 based PCB process. And in the comparison, what could be seen was that if the etched copper in the conventional PCB process is replaced with printed silver conductors, the global warming potential is already reduced to about 1/2 of the original. And then further, if it's possible to replace the FR4 with flexible substrate, either polymer-based PET or paper, the global warming potential is even reduced more, and it is going us down to 14–15% of the original, which is of course very nice. And yeah, indeed, the benefits, which actually I didn't mention earlier, this in addition to compatibility with several substrates, it also is beneficial that you can quite often work with mild solvents, which is very nice from the work safety point of view, of course. Yes, and okay, the process is pretty good from sustainability point of view. And in the same project, we then compared the kind of investigated LCA of the smart label, which was kind of like our example case in this project. And it's a smart label for temperature monitoring during the logistic chain. And what could be seen in this LCA study was that most of the environmental load in this case comes from the printed electronic inks, the conductive inks and adhesives. It is this green bar here. The yellow one is the energy used in production, so that is also quite considerable. And then also some parameters are contributed quite a bit from the substrate material, what is used. So basically, we know now that the process is pretty good selection, that we have selected this printing based fabrication. But also we wanted to look at the conductive materials and the substrates. And regarding substrates, very typically in flexible electronics, if the material doesn't need to stretch, the PET is the conventional plastic which is used in printed electronics. But it is possible to replace that also with some renewable materials, like even the PET can be based on renewable resources. It doesn't need to be fossil-based. But we also looked, for instance, at the cellulose acetate propionate. And in the example, which is shown in the picture here, it can be seen that when the conductivity or the resistance of a kind of print pattern was compared between these two substrate materials, it could be seen that the resistance was decreased when the material was changed from this PET to cellulose acetate propionate. And actually, this is really nice observation, because it means that we don't need to compromise necessarily in the performance when we go from conventional fossil-based material to bio-based materials. But what is important, of course, is to look at the compatibility of the material with the processing parameters and also the application specific use. So for instance, if the end product is going to be exposed to temperature, humidity, and light, then those tolerances need to be taken into account, of course. Then a little bit about the conductive materials. So silver is used as the, let's say, like the state-of-the-art material in printed and hybrid electronics. So it's easy to process, and it's very well available. And also the conductivity is good. But especially when we have a structure which includes a printed antenna, there is quite a bit of environmental load from the use of silver. And of course, if you can recycle the silver from the printed structures, that's great. But at the moment, it might still be a little bit challenging to achieve. But also, if you can think about like replacing at least part of the silver with another conductive material, that would be beneficial, or if it's possible to decrease the use of silver. So in this picture, for instance, it's shown that if we go from silver-based printing patterns to copper-based silver patterns, so this is printed copper, not etched copper, or to printed carbon inks, the CO2 equivalent is decreasing considerably, but this doesn't take into account the fact that the conductivity of copper and carbon is not on the same level with silver, and in some printed structures it's not even possible to use other materials, but sometimes if there is if the space is not limited and you don't need to go into extremely low line width, so it might be beneficial to consider replacing at least part of the silver with another conductive material. So I still want to continue a little bit about this material selections. So this is a work by my colleague Maria Välimäki, who has been studying a lot on the printed OPVs, the solar cells, and has been looking at the possibilities to replace the materials with more let's say environmentally friendly options. And in this study here, the LCA study, what could be seen that the reference structure, when it is changed to a structure where the silver, instead of being like a compact surface, has been applied as a silver grid. So already this change is considerably decreasing the CO2 equivalent of the printed OPV. And then further, if the silver is then replaced with other conductive materials, then that is really putting the environmental impact downwards. So that is always good to think about the amount of silver what is used and how it could be reduced, and if there are any options to replace it with other conductive material. That is great. Then I would like to talk a little bit about biodegradation or biodegradable electronics. So or transient electronics, and regarding this topic, we have investigated like solutions where the printed circuit together with the assembled components have been deposited on nanocellulose-based substrate. And this system, what is demonstrated here, it's an EGC measuring wearable, and basically what you can see that when you expose to this system, this nanocellulose system to soil, the substrate is disappearing after a while, or it can even be repulped in water, and you only at the end of the repulping you can see the conductive printed leads as well as the components. And this is especially beneficial in such applications where there is a possibility that the item is going to be remaining in natural environment, or if there is a decrease of risk for microplastic release, and also it is also one way to let's say introduce new strategies for chip recovery. So this is also something to consider, and it might not always be beneficial to degrade the substrate. You can even recycle it, but this is also a good way to let's say recover the conductive materials. A little bit similar approach has been taken in an ongoing KISTERA project, Tesla Transient Electronics for agriculture, and in this project it's more or less the same. The device is a little bit more complicated. An energy autonomous self-powering sensors for plant condition monitoring, and in this case the device contains the OPV, again printed supercapacitors, reusable electronic module. At the moment it's reusable. In the future it might also be more transient, and then transient sensors for the plant conditioning monitoring. And VTT's role in this project has been in the development of the transient soil compatible OPV, and that is like a continuation of the earlier OPV work. And now we talked quite a bit about this smart label, and the ecotronics project has been mentioned in a couple of slides earlier. And I would still like to say a couple of words about the use case for this label. So of course it is clear that the fabrication of the label has a certain environmental impact, but it's good to consider also then that what is the effect of the use case or the use phase of the item what we are developing and producing. And okay, so here is like the greenhouse gas emissions from the fabrication, but it has been calculated that if this label is capable even to reduce the amount of shippings during the transportation, it is already overcompensating the environmental impact in the manufacturing phase. And of course, if you are able to decrease the food waste, which is a considerable issue, so that is even giving more overcompensation to the fabrication of the label. So you always need to think about also the use case when you are looking at the environmental impact of the fabrication of a certain item, and this is very, very important as well. So this similar approach we are currently also taking in another project, European project called Super IoT or SuperIoT, and in this case we want to extend the use of this kind of small low-cost sustainable IoT devices for different applications, like in addition to smart packaging and logistics, also to climate environmental monitoring, different home workspace environments, wearables, smart cities, and so on. And in this project, what is then new? In the previous one, in this ecotronics, we had the silicon-based components, but in this project, we are also looking at really like printed electronic devices like diodes, and want to create or want to use printing to realize part of the electronics. So this is ongoing as well. And for that purpose, we are currently investigating at VTT a very unique printing method. Reverse offset printing is the name of this method. And what is so unique in this is that it is possible to produce or to print lines which have a width of about 1 micrometer, and this is not very usual for the printing-based method, and this is not a reel-to-reel method. It's a sheet-to-sheet method, and I will show a small video on how it works. But it is really suitable to produce really thin lines, and can be applied in the printed electronic devices like TFTs, but also transparent grids, anti-counterfeiting, sensor applications, and so on. And I think the video comes now. Yes, and I will first explain a little bit because it's pretty fast. So what happens first is that the ink is applied on a PDMS blanket through capillary coating, and then this blanket is patterned with a kind of like the printing plate which has a negative image, and then the blanket has this semi-dry, this PDMS blanket has the semi-dry ink, and that is then further transferred to the substrates, which can be basically anything as it is smooth enough. And I will now show the video because it immediately starts with this ink application on the PDMS blanket. And now we have the patterning of the PDMS blanket. You can see the pattern is appearing, and okay, now the plate is removed and the substrate comes instead. And now the ink is transferred to the substrate. In this case, it is glass, but it can be anything smooth. And then here we have the devices, and it's then taken to the inspection. And indeed, the lines are about one line width about 1 micron and alignment about 2 microns, and can be indeed applied in different applications in the devices. And indeed, as mentioned, this is very unique printing method. So basically, the outcome is very similar to photolithography. And if you compare it to other solution deposition methods like inkjet printing, gravure printing, flexography, the line width is much thinner. And also, what is very unique is that the printing pattern has very distinct edges. So it's really very sharp, and this is very nice property as well, as you can anticipate. And here are some examples where it can be used for metal electrodes. For instance, for multiplexed sensors, this is like a cold pattern multiplexed basis for multiplexed assay for biomolecule immobilization, metal meshes for heating applications, transparent antennas as well, and then indeed metal oxide and organic polymer-based TFTs. So these are the applications, and the idea is to exploit these two solutions, which include more printed devices, not only silicon-based. And then I would like to briefly talk about powering and the batteries here. So we are also looking at next generation batteries at VTT, especially in collaboration with our colleagues working with sustainable materials. So this is showing the process. Starts with the electrode slurry preparation, and the slurry can be based on for instance, biocarbons. And then the electrodes are coated with slot die coating in this reel-to-reel printing line in our pilot factory. So that's taking place here. And then comes the manual phase. So at the moment we are assembling the batteries manually, but also here we want to go into more automatic procedure. So basically what you do, you cut the electrodes and then stack them on top of each other. And this can be done in the normal atmosphere, of course, depending a little bit on the chemistry. But then it is put into this encapsulation material and then taken to the oxygen-free argon glove box, where it is sealed and then it dried, and the electrolyte is filled in. Okay, now it's vacuumed a little bit. Electrolyte goes in, and then it is sealed. And indeed, basically, we can do both these pouch cells and also the coin cell batteries at VTT, and we are exploiting here the new materials from our colleagues. And then after this is ready and sealed, it can be again taken out, and then the power source will be characterized in the cycling system. So this is how the batteries are assembled by us. And regarding the sustainability in this battery area, okay, other colleagues are investigating the circularity. For us, the focus is more on the selection of materials, like replacing lithium with sodium, graphite with lignin-based hard carbon, and also using cellulose-based separators. And then this processing using this reel-to-reel printing, also dry coating without solvents, and also what we have been looking at, the increase of the lifetime of the batteries by different strategies which are preventing the dendrite growth on the electrodes, and this is beneficial from the lifetime of the battery electrodes. So this is investigated in several EU funded projects. Then finally, maybe briefly still, a couple of words about our GreenTool. So as we have already seen, there are several aspects which should be taken into account when you are considering the sustainable fabrication of flexible electronics. And okay, LCA is kind of very useful tool, but normally in order to implement the LCA assessment, you need to know quite well that what you have done, and you need to know the materials and how much and so on. But we wanted to have something for the design phase, something a little bit like streamlined, so that we could already from the beginning make some selections towards more sustainable approaches. And so we developed and published a Excel-based tool, what we call GreenTool. And this is very much based on the Eco-Design Directive, Sustainable Development Goals, and Green Deal. And basically, it's an Excel-based tool where we have 7 main criteria listed here, from raw materials, manufacturing, logistic use, end of life, and also this kind of like overall category sustainability maturity. And each of these criteria are then divided into several sub-criteria, which are all described in the publication shown here. And what we do then when we are kind of considering a development of a new flexible device, or actually it doesn't need to be flexible, but a new electronic device, we kind of like select a benchmark like in the case of smart label, it can be a data locker with coin cell batteries, and then describe the processes or the anticipated processes for next generation products, and then we start looking at this and start benchmarking and comparing these new developments against the state-of-art benchmark. And we score each of these new concepts against this benchmark with a score where 3 is similar to the baseline, the benchmark, and 1 and 2 are worse, and 4 and 5 are better. And these are then evaluated for each of the sub-criteria. And we have done this for the smart labels. This has been explained in the same paper where we explain the methodology. And in this case, we were indeed comparing the state-of-art data locker with printed locker with flexible batteries, a printed locker with OPV-based energy harvesting, and then the same one but with environmentally optimized materials. And here what we could see is that regarding raw materials, where we could see the biggest differences, the differences come from the possibility to use renewable abundant raw materials in manufacturing. The difference comes from additive manufacturing. In logistics, mainly from the lower weight and possibility for non-distributed manufacturing. In the use maintenance, mainly from battery recharging, and in the lower cost and maybe more safe to use usage in use phase, and circularity, from circularity possibility in the end of life phase. And the drawback in the new developments is the limitation in the material availability. So this is a tool where you can really think that what are the areas where you could go towards more sustainable developments. And then we did the same for the batteries as well. Then we modified this assessment matrix a little bit, and in this case we had 2 state-of-arts, like lithium-ion battery with cobalt on the cathode and cobalt-free cathode, and compared with those a lithium metal battery and sodium-ion battery. And in this case, what we could see, I'm only saying it very shortly because I can see that I'm running out of time. But here what we could see was that the new technologies have different strong areas, like for instance the sodium-ion battery has benefits in the raw materials, whereas the lithium metal battery has higher energy density and has improved better safety, and this is actually, I think this should work for everybody, the link here. So this is explained in the conference paper presented in Electronics Goes Green conference last summer, and this actually got a best paper award in the session. And if this is of interest, you can find the details in the paper here. And yeah, what should be said regarding these new battery technologies is that for sure here, especially the end of life management is not very mature yet in comparison to the state of art batteries. And yeah, now I'm actually coming to the conclusions of the presentation. So I'd like to say that the sustainability and circularity in electronics need to be tackled without delay. And the materials and the manufacturing methods are in key role, essential role, and also the eco-design. The design phase is extremely important. About 80% of the environmental impact is decided already then. And now we have a very simplified benchmarking tool which can be used the decision making already in the design phase. And yeah, I would like to thank you, of course, for listening, and also I would like to thank my colleagues contributing the work presented here, and all the projects and funding organizations. Thank you very much.
Well, thank you very much, Maria. That was an interesting talk. If you could take a moment and paste the link to your paper into the chat, that would be good.
I will, yes, of course, yes.
And I've pulled up the Q&A, and it looks like I'm the only one who's put questions in there, so I'll ask one or two and see if anyone else joins in. Again, you talked about silver being your most common and useful trace material. What other materials can be used on one hand, and which ones are able to be applied on the other hand?
No, I would say that the second option is copper. But if we talk about, okay, copper can be used as like, you know, for instance, as transferred metal foils, but of course then it doesn't, it's not exactly the same as printing, but quite many applications are possible with the transfer foils. Then we can also print copper inks, and there is all the time more and more copper inks available. But the processing of the copper inks or the sintering of the ink is not as straightforward as with silver. So it can be done. There are possibilities like combination of heat and pressure or photonic sintering, but there are some challenges in for instance in the oxidized surface of the copper traces, but I think this area is developing also rapidly, and all the time more and more possibilities. And then of course carbon-based inks, and also there are some inks which contain a mixture of a metal and carbon, which also might have a conductivity which is sufficient. So there are different options.
As a microwave engineer, I really need very, very high conductivity, but I think for a lot of DC applications or low frequency, a higher resistance can be used.
Yeah, depends always on the application. Yes, for sure.
Yeah.
Yes.
But again, going back to the fact I'm a microwave engineer, gallium arsenide is one of the chip materials. There isn't a lot of gallium arsenide even in the phone, but the question is, do you know if gallium arsenide can break down into gallium on one hand and arsenic on the other hand in a landfill?
Oh, I'm sorry. No, I don't
Okay.
have information on that. No, sorry.
That's okay. You made these spider plots or radar plots. Is it possible to somehow use AI to get more information or more accuracy on those sort of things?
No, we have actually been thinking about that. At the moment, we haven't, but yeah, yes, it has been in the air, but so far no possibilities to do that. But I agree that would be very interesting indeed. Indeed, what we are at the moment trying to or initiating is that, okay, so far we've used it for the flexible electronics applications, but as VTT is doing a lot of microelectronics, kind of like conventional semiconductor work, we are also now looking at the possibilities to implement the tool for other electronic applications as well, of course, after some modifications.
Dialan and Feng Yuan, I see you have some questions, but I can't actually access them. Dialan, why don't you ask your question and then Feng Yuan?
Yeah, Charlie. The question I had was, it was a very interesting talk, and I wanted to ask, what's the safe degradability or sustainability of these inks you used in your printed technologies?
Oh, sorry, what is the
Degradability, or I mean, if you want to post service, you want to degrade the ink safely
the metal?
and reuse it.
Yeah, no, for instance, the silver ink, it doesn't degrade. It doesn't degrade. So it remains like. Let me show again this one picture which I had. No. So basically when the substrate is biodegrading, the silver remains intact, which is actually good in that sense that you can consider like recovery of the material. I think we are now coming here. Like, okay, can you see the? I think I'm still sharing. Yes. So basically, what you can see here are the parts of the printed circuit, so that remains intact, which is in that sense it's good that it can be recovered.
Okay. Okay, thank you.
You're welcome.
Do we have time for one more question here, or we need to move to the next
I
one?
think we're doing okay, Feng Yuan. Why don't you ask the last question?
Okay, sure. Thank you for your nice talk. And so for now, we have seen many papers on printed electronics, but in terms of the real products, there may not be so many products based on printing. So what do you see this? How do you see this?
I think that regarding the applications like the wearable electronics is definitely an important one, because what we can, I didn't stress that in this presentation now because this was more for the sustainability, but what is, for instance, possible is to print these conductive circuits on stretchable materials, and this is of course increasing the usability of the wearable patches. For instance, you can have like electronic tattoo type structures on skin, or like for instance in this picture there is this nanocellulose based patch which is very conformable. So and this can be on the TPU as well. So TPU has been the main substrate for the wearable electronics, and what we can even combine with the wearable devices are like in addition to conventional sensors, also like biosensors for the metabolite. So I think that this wearables is definitely the first application, but then all kinds of smart labels, that's very important as well, because there you want to have like lightweight items which are also need to be conformable and can be attached, for instance, on a surface of a package. That's one area. And then also this printed and hybrid electronics is used as let's say kind of as a starting point for structural electronics, when you can like on top of the let's say this kind of device, what we actually now see in the picture, you can even encapsulate that into a mechanical structure. So for instance, in a car electronics can be embedded in the mechanical parts of the car, like car door or this dashboard or things like that. So that's an important application as well. Yeah, I think those are like among the most important ones. And then of course, if you need like large areas like solar cells which are retrofitted and which need to have a very low weight, that is important application as well.
Okay, well, thank you very much. We'll wrap up your session. Again, I want to thank you for an interesting talk.